Now let's look at some specific heterogeneous MPNNs, and we'll start with the relational graph convolutional networks, RGCNs. Okay, and here you can basically see that we are doing what we did in the homogeneous case, but in this case we have a separate summation for every label tau prime in this L bidirectional E. Okay, so for every label, we have a separate summation, okay, over the nodes that are connected to you through this tau prime, with its own normalization and its own weight matrix. Okay, so this is W of tau prime. So different tau primes have different weight matrices, disjoint set of parameters. Okay, so really straightforward extension of the homogeneous case. Of course, on top of that, we apply the activation. Okay, two things regarding the normalization factor. So one, do not worry about the case where, n tau is empty, because then we do not sum up over anything. So this is fine. And also the paper talks about the possibility of learning a normalization factor C tau instead of using some fixed one like the number of tau prime neighbors. Okay, here's another example, the Hans, heterogeneous attention network. And here we're basically having two levels of attention. Each node attends to its tau prime neighbors. Here it's called phi 1 and to phi p. I'll explain later why they use these phi 1, phi p. But think of these now as just tau prime. This is a figure from the paper. Okay, so first aggregating over the nodes of the corresponding type. Okay, and then doing attention on every neighborhood, and then an attention over all the tau primes. Okay, this is the second level, semantic level attention, where we attend to the different tau primes given the values that we got from the previous layer. Okay, so now I write it in text. We have the two levels of attention, node level for each tau prime attending the nodes that are connected through tau prime. And the semantic level where we attend to the different tau primes, okay? Basically aggregating the values that we got from the node level attention. Okay, so that gives us like two layers. Now, two strengthening, they, as usual, talk about or extend their model to allow for multi-attention. And also, instead of looking at neighbors, they look at the paths of metapaths. Okay, or nodes that are connected through paths that correspond to metapaths, just like we've seen previously. So this is a rather standard extension. Okay, let us recall what a metapath is. So a metapath, I remind you, this is simply a path of labels, okay? Meaning that it refers to paths that start with the node label sigma 0, then go through the edge label tau 1, which can be in one direction or the other direction, then going to sigma 1, and so on and so forth to sigma k. Okay, so here, this is the definition that we've been using previously. And this is an example, the usual example that I give. This is a heterograph and this is a metapath. These are two metapaths, and we can see different paths of the heterograph corresponding to each of these metapaths. Okay, now how do we enrich a heterograph with meta paths. So basically, instead of looking at neighbors with respect to some tau prime, we look at neighbors with respect to phi, okay, which is a meta path. Okay, so this is basically, a natural extension of the labels. This L, the bidirectional arrow. Okay, uh, and N phi of U is a set of all nodes V that can be reached from U through a path that confirms to phi. Okay. Uh, so several ideas in papers that or in architectures that use metapaths. So they usually have some predefined set phi, bold phi of metapaths, okay, and they traverse the relevant finer neighborhoods of every node. Okay, so they go through all of these non-bold phis or small phis in the set of metapaths. And it's not just, to generalize the idea of looking at immediate neighborhoods through edges. Okay, so this is another way of describing the Han now with the metapath. So this is uh, you have P metapath phi 0 to phi P. And again, node level attention where we basically focus on one metapath and for each node we aggregate the uh, the nodes we attend basically to the nodes that are neighbors through this metapath phi 0. We get a value, okay, z phi 0 to z phi p, and then with these we again define queries, keys, and take the values and sum them up here in this summation uh, in another layer of attention. Okay, so first the metapath attention, the node level attention, and then what they call the semantic level attention, where we attend to the different metapaths. Okay, that gives us a value, and then some decision layer MLP in the final value. Okay, here's another architecture, AGT. Okay, based on the multi attention. Here, all the neighbors are attended. Okay, so we are mixing between nodes of different labels. Um, but the computation of the keys, the queries, the values, we need matrices for them, weight matrices. These are label specific parameters. Okay, and again, we can generalize, or they generalize from labels tau prime to metapaths phi. Okay, but I don't use these two levels of attention, but rather one level of attention. Um, and the paper also talks about ways of learning or choosing wisely useful metapaths. Okay, so this is how it looks like. Okay, the AGT, and so it's basically like that. We have we have two neighbors, V1 and V2. They are called here S1 and S2. And here we have a layer that computes the query and key for each neighbor. Okay, for this is for uh, this is basically computing the attention of uh, um, the attention of V1 and V2. Okay, so this part computes the queries and keys and basically produces from them the weights of the weighted average. Okay, so this is the attention. Okay, attention for each of the vertices. This layer takes these values from the previous layer and computes the values. Okay, so we apply here some linear, some transformation, we get the values. Okay, then the usual mechanism, multiplying the attention with the value, okay, and taking the average, the weighted average. Aside of that, we apply some nonlinear activation, and all of these things will repeat in several layers, okay? And then we get the final layer, which they leave here generic as, you can use it for whatever downstream task that you use uh, for your prediction. They have here the backward edge for back propagation or the backward computation.